Okay, we can go ahead and get started. Good morning, everybody. Welcome to Space Safety and Traffic Management. We'll be having two speakers today. First up, we'll have Graham Wild. Dr. Wild is a senior lecturer in aviation technology in the School of Engineering and Information Technology at the University of New South Wales, Canberra. He has also been research with the CSIRO Electric Machines Group, the CSIRO Intelligent Systems Group, the U.S. Naval Research Laboratory, and most recently with the Laboratory for Active Materials and Smart Structures at the University of South Carolina. Welcome, Dr. Wild. You may go ahead.
Thank you very much. So what I'm going to talk about today is a post-accident analysis of fatal space-related operations and activities. So first, obviously, it's great to go after Colonel Mike Mullaney there, who touched on a few safety-related things, especially with the space shuttle. And the image you can see here was something the Colonel also showed in terms of the Falcon 9 explosion in 2016. One of the things I want to make very clear here is that I'm not an authority in safety. I'm a technologist, as I'll show in a second. And what this is about is understanding what safety looks like in the aviation industry and what sort of things need to be knocked up a notch rather than needing to be built from the ground up, because even companies like SpaceX have their own accident investigation team. So not only is NASA and other government organizations doing great jobs investigating accidents and things like that, there's also things going on in terms of private companies having a look at safety, and clearly it's very important. I've always said that if we have the incident, for example, that happened a few weeks ago with the Blue Origin launch, that would have been quite disastrous if there'd been people on board in terms of the reputational damage to the company. So even companies who want to make a buck from going to space, they're still obviously very important for them to do it safely, because otherwise they're not going to have customers coming back to them. Even people who are putting multi-million-dollar satellites into orbit are giving those to companies who are going to safely get those things into orbit. So just a bit about me. So I'm an aerospace scientist and technologist. So I like to say I'm not an engineer. I've got my undergraduate degrees in physics and mathematics. My primary area of toys to play with is optical fibers and lasers, so photonics and optoelectronics. And my PhD was in aerospace vehicle health monitoring. So I like the concept of giving an aircraft or a spacecraft a central nervous system so it can detect when things are wrong with it. So the underlying principle of this sort of technology is giving something like the space shuttle the ability to detect and assess its own damage, like those foam impacts that were mentioned before by the Colonel. And there's me with my family. There I am with my daughter in front of the Discovery out at Dulles at the Smithsonian there, as also mentioned. And there's me with my family. Just recently, I was at the AIAA Aviation Conference in Chicago, went across to the United States Air Force Museum, and we're in front of the XB-70 there. So as mentioned before, as introduced, I did my postdoc after I finished my PhD, then became a lecturer in aviation systems, and it was just by coincidence. And now I'm a senior lecturer, specifically focusing on aviation technology. And obviously the hybrid there between air and space, aerospace, it means that some of the technology stuff they do also crosses that border. So in terms of my research background, I've got more than 170 publications. As mentioned before, in visiting research at multiple places. I forgot that UCLA, when I wrote that little blurb, I also visited there and did some work with the Active Materials Lab there. And I've got a very diverse kind of background. So that concept of me calling myself an aerospace scientist and technologist, I enjoy a lot of different things. So while I love being at an optical table playing with optical fibers and lasers and things like that, that's that bottom left image there. I also do odd things like take my partner on a romantic trip to Paris and at the Eiffel Tower, which you can kind of just make it. I'll see if I can get this to work. If I can get it to work, or at my pen. We are here. We are working. So the Eiffel. I don't know where I am. Where here's the Eiffel Tower is just there, and instead of taking pictures of the Eiffel Tower of my beautiful partner, I'm busy taking pictures of contrast in the sky, because I'm interested in the environmental impacts of aviation as well. And the bottom corner there is my son wearing an eye tracking headset flying a drone. So again, anything to do with technology and science in aviation, numbers, especially with my maths background, I love playing with all those sorts of things. And so coming into safety is an interest in numbers and methodologies became very useful to look at safety data. So why do we care about safety? I kind of alluded to this before. I mean, space commercialization, the more things we do in space, the more important it is for us to do things safely. So space commercialization activities are going to include space tourism, suborbital, orbital, and even lunar and beyond. Again, as mentioned before by the Colonel, Blue Origin's got their own lunar lander they're still progressing with. Elon Musk is talking about going to Mars. So there's definitely is that lunar and beyond prospects there. There's also transportation, so legacy space plane type things, effectively what the space shuttle was, and then point-to-point space travel. So one of the ideas for the super heavy is to do point-to-point space travel, so 60 minutes to most destinations around the world for effectively twice the cost, I think is what the estimate was from SpaceX. So it's going to be a huge boom there and a huge competition with business class travel in aviation. The next aspect there is space manufacturing, and I couldn't help but include an image there of a Thor Labs collaboration with Made in Space, optical fiber manufacturing for Zeblan fibers, so special crystal fibers that need to be made in microgravity. So another way to make money in space. And the last one that people love to talk about is space mining, so the amount of money that's out there. And I wrote a wonderful little article for a trade publication here in Australia talking about space mining and what the role of a space force would be in those sorts of activities, kind of harking back to the 16, 17, 1800s and the roles of navies and commercial shipping and things like that. So in terms of space tourism, again, hopefully most people are aware of this in their history. So it's quite long now. So it's over 20 years ago when Dennis Tito first got to fly up to the International Space Station as the first space tourist, and a number of people got to do that between spending between $20 and $40 million to spend between 7 and 14 days on orbit. So a great opportunity there. And then it kind of died off, and now we've got this wonderful situation last year where we got what I call the year of civilian space 2.0. So there's resurgence of space tourism. Virgin Galactic successfully launched last July, Blue Origin as well. Obviously a bit of rivalry between them and everything about you're not going to space, all that sort of stuff. It's great. And then obviously SpaceX's Inspiration 4, actually orbital-based systems, not just suborbital. So this is reality as it is today, and these are important things for us to look at. And what the growth in the commercial space industry means is it's going to start looking a lot more like the commercial aviation industry. So we're talking about travel for tourism and for business. We're talking about freight and cargo, manufacturing, lots of just-in-time logistics and things like that. So it's the concepts that we use in aviation safety will need to be applied across into that global space-based thing. So we need an international space organization, just like we have an international civil aviation organization. So let's have a quick look at substantive aviation safety and what a post-accident analysis looks like to give you an understanding of what we can do when we have a look at space. So here, one of the things that you might commonly read about is the term crash, and it's something that we can use almost every day when we talk about cars and things like that. It's very kind of synonymous with an impact, but bad things and fatalities that happen in aviation usually aren't associated with aeroplanes crashing into the ground, into trees, into buildings, or into each other. So a crash is not a term that we use, although you'll still see it. Some people use it in the literature. It's definitely not something we use. So we talk about safety occurrences in general, and then in those safety occurrences, we have accidents. And an accident is a safety occurrence where someone is fatally or seriously injured, or the vehicle is effectively fatally or seriously injured. So there's a structural failure or major damage to the airframe, or that vehicle is completely lost or inaccessible. So if it's crashed in the top of a mountain or the bottom of the Marianas Trench, you're never going to get to it, and there's nothing you can do about it. So that's definitely an accident. And there's going to be fatalities there anyway, unless it was an unmanned cargo transport. Incidences are safety occurrences other than accidents, and then there's the serious incident, which is the type of incident that effectively looks exactly like an accident, but there is no injury, fatality, or damage to the aircraft. So it's just effectively sheer dumb luck has resulted in something happening and no one getting hurt, and they're very important. So understanding all of these things, that even that level of minutia that's in incidences, such that for every 100 accidents, there's tens of thousands of incident reports. The amount of data and the volume of that data that we collect in aviation is what enables us to be the second safest mode of transportation in the world. And I don't know if you've heard people mention that before. Some people say it's the safest, and I like to remind people that the Japanese Shinkansen actually hasn't had a single fatality since 1954, since it started operation. So sadly, they are the safest, and we are the second safest in the aviation industry. So there's going to be a huge push to try and get these sorts of levels of reports filed as well in space operations, so people can learn from incidences before they turn into accidents. And again, they kind of mentioned a few things that are very relevant to that in terms of there were lessons to be learned, but people chose not to learn those lessons.
Dr.
So if you have a
Lau,
look,
sorry to
sorry?
interrupt. Simone Castro had raised their hand earlier. Simone, did you want to ask a question?
Yeah, feel free if you've got a question at any point. Yeah.
If not, we can go right ahead again. And for the audience, we can also do the Q&A option right at the bottom. So go ahead and type the questions out or even in the chat, and I will read them out right to Dr. Graham afterwards. Dr.
Perfect.
Graham, you can go.
Thank you. So if you have a look historically, you can see here since 1946 what the accidents and fatality counts look like in the aviation industry. So obviously we get a pickup in fatalities as aeroplanes got bigger, but overall the number of accidents have been decreasing. So while fatalities got increased, that was just basically because more people were sat on aeroplanes. And then now the number of people sat per aircraft is basically constant, about 160 passengers per aircraft per flight on average. They're now effectively lockstep with each other, moving down. So the next thing for us to consider is the growth in the industry. So if we have a look here, you can see huge growth in the amount of passenger traffic we get. So we talk about RPKs in the industry, revenue passenger kilometres, so how much money making kilometres times the number of passengers we carry in the aviation industry, and also the number of departures, actual number of flights that there are. And if we combine those previous two plots, we can have a look at our actual accident and fatality rates, and we can see lovely trends there. That's a logarithm scale on the left, and you can see these lovely linear trends. So the exponential decreases in all of them, and obviously the exponential decrease is driven by the exponential growth in the industry. But that's still an achievement, that we're doing so much more without an increase in the number of accidents and fatalities associated with that. That's not homogenous across all types of accidents. In fact, I've done some studies that have shown that while overall accidents is decreasing, there are some issues with some technology aspects that are growing, things like maintenance, for example, where we see a growth rather than a reduction, not in the rate, but in the absolute number. Another thing we care about, for example, is the type of vehicle that's involved in safety occurrences. So here's just a quick snapshot of things from the ATSB and a breakdown between whether they're accidents and incidences or serious incidences. And you can see that, again, in the large commercial transport that we do here with aeroplanes, a large number of instances are reported, small number of accidents occur, and we're able to keep that huge gap between them by knowing a lot about those instances and everyone trying to learn from them. If you go to the right-hand side there, where we look at RPAS, or remotely piloted aircraft systems, where we're much newer technology, get a lot more accidents. And I think that's kind of like what we see with space at this point in time, and what we noted with hypersonics in a previous publication that we did, is that these newer technologies that are not so rigid in their aviation safety thinking, accidents are heavily reported, heavily investigated. Everyone's very aware when someone dies, sadly, but that's not what makes things really, really safe. It's knowing about the benign things that people don't want to waste time writing a report about that becomes more important. So that yellow bar there is small just because people choose not to report it, and that's why we need to make sure for space where we kind of adopt those sorts of philosophies such that everyone can be aware of any and all near misses and slight hiccups that come up in terms of safety. Another interesting thing that we can talk about is whether or not it's human factors, or the pilot or the operator or people involved, or the technology itself. So here you can see on the left a famous statement from Boeing drawn out, which is that in the beginning of aviation, equipment problems were responsible for the majority, 80% of accidents, and human factors were only responsible for 20. And you jump forward to today, and it's human factors are responsible for 80, and equipment problems are only responsible for 20% of accidents. And if you have a look at newer technologies, again, in a previous study we did with drones, with RPAS there, you can see a much larger skew to that equipment problems, and same with our hypersonics study that we did last year, a huge skew into the technology. So these newer areas, you see a lot more technology issues, and that effectively mimics the beginning of manned aviation, what I should call crude aviation, so conventional aviation in the good old days. And obviously over time, hopefully we'll iron out some of those technological problems and make systems safer and things like that. But the same thing obviously could be expected to be true for space-based systems. So just quickly need to mention the ways that we can look at these things. So the ADRIP taxonomy is what we normally utilize when we're having a look at these things. And there's a lot of parameters and properties that we can categorize. So we can have a look at the type of aircraft, the type of damage, what phase of flight was it in, where was it, and probably the most important one there is the occurrence category. So what type of accident was it? So that's this one here, and we'll have a look at that on the next slide. And that's why we're talking about this at this point. So here we can see a list, and I don't expect you to read them or understand all those abbreviations, but we get out, importantly at the top left there, things like system component failures. So when things go wrong, those equipment problems and related things. So loss of control as well, an issue, fire, big issue, and that's at the top there for conventional aircraft, and also a common issue that we just noted with space-based occurrences. And there's a long list of others. And again, we don't need to understand all of them, but we can look at a spread of accidents in the aviation industry and have a look. And we see a lot of these things are technology related. A lot of them occur in our critical phases of flight during takeoff and landing, and they can be, a lot of those can be pilot error type things, and then a few of them are environmental issues. And it's this slide here that actually makes me think that Boeing slide is probably not quite right, because I think those environmental issues account for more than 20%, and I don't think you can claim that a bird flying into you is a pilot error. So it'd be actually interesting to have a look at those numbers. So what did we do in this specific study? So we went through a data source, and to be honest, we started with Wikipedia and the great articles that are the entries that are in there in terms of looking at accidents. And then we went through and we corroborated that data with the previous database that we used for the hypersonic study, which is the Astronautics, as a great database in terms of almost every space launch and space activity and rocket launch, rocket activity from a large scale. It's a fantastic resource. And then we were able to go in there and clarify things. So I did actually note a few errors and mistakes in those Wikipedia lists, things like that. I should actually probably do the community a favor and go back in and edit them, because a few of them had their fatalities and dates and things wrong. And obviously with NASA, we've got some great data out of NASA. And effectively what we were doing is going through and having a look at simple things like who, what, where, when, why, how of those safety occurrences, specifically accidents. And then we were applying the ADRIP taxonomy to see if it was applicable and to work out how we would need to improve it for a future commercial space safety reporting system. And I note there at the top, this is a deductive coding. So we're taking those previously existing taxonomies and we're going to apply them directly. And there's a little plus sign there, which again addresses that bottom point where we might need to make some modifications to it. When it comes to analysing the quantitative data, we're effectively doing a Pareto analysis. That's the concept where you can, in quality control, you talk about 20% of your effort results in 80% of your results. So what we normally say in sorts of the concept with accidents is that 20% of the type of accident are responsible for 80% of the total number of accidents. So if you focus in on those larger things, you get bigger gains in terms of improving quality control. That's exactly what quality control people do in terms of understanding where the quality deficiencies are and tackling that and doing all the Six Sigma type stuff that they love. And that's a little bit out of my wheelhouse. But wonderful tools to use to qualitatively and quantitatively analyze the data. So let's have a look at some things that we noted. So here we've got a longitudinal analysis. So we've got decade on the bottom. So we're just looking at the trend, or trying to see if there's a trend in our fatal accidents as a function of decade, just because the granularity is not enough for us to just consider years. We know here we get 4 of them in the 1930s, and that's obviously a lot of pre-World War II-esque experimentation going on. So mostly lab-based explosions and things like that with rockets. And then we move into the second section there, where it's almost homogeneous. So I think if I put a regression line on top of those 6 data points, it would not be statistically significant. So there's no huge spike. It's a lot of noise there, and it's a kind of an interesting trend. It's not gone up, it's not come down. And then if we overlay that same thing that we noted before when we looked at the aviation data, if we overlaid traffic and industry growth, it's actually quite good that that number hasn't grown, because the amount of space activity clearly has grown over that period as well. Same thing if you look at fatalities. Again, no huge trend there in terms of it's not going upwards, it's not going downwards, but we've got more activities going on with space. So the number of people involved in those fatal accidents that have died has reduced. And I will note here, there's a couple of incidences in China, for example, where things veered off and landed onto villages, and reports in both of those two cases suggested up to over 100 people had died. And I've used the lower bounds of 20 and 6 each for those two specific accidents. And I've tried to be conservative where possible, so make sure nothing looks too out of the ordinary. If we have a look at the dichotomous features, so different aspects of the accident cases that we looked at, obviously, since we only looked at fatal accidents, it's not a surprise that the first two there are 100% or 55 of the cases are fatal accidents, because that was the criteria. And then interestingly, about 24% of them involved fatalities with crew, and far more, 76% of them, 3/4 of them involve fatalities with support people, or if you break it down to crew, people on the ground, and people completely devoid, so civilians, bystanders, villages in a few hundred kilometres away, those people actually account for 15%. So if you have a look at it in terms of the number of people that have died, 15% of the total fatalities have been crew, 15% have been uninvolved people, and 70% have been ground workers and operators. So it's actually, interestingly, much more dangerous for the people on the ground than it is for the people on top of the rockets. Whether the rocket was at fault or not is another interesting feature there that I would not have guessed. That is, the rocket was only at fault 1/3 of the time, and 2/3 of the time it was something else that was responsible for the fatality or the fatal accident. So again, quite interesting. Where it's not a huge surprise that the USA is going to be the biggest openly reporting things, plus lots of operations, so not a huge surprise, followed up by Russia and then tailing off quite quickly. So very focused, heavy there on the USA. In terms of what we note in terms of that graph, that very complicated graph I showed you before, it's very similar in terms of those system component failures, the non-power plants and the power plants, but also interestingly, because there's a lot of accidents with the people on the ground, that ramp, which is effectively the ground handling, the refueling, all that sort of stuff, that's a huge spike that's very different to what we see in aviation. And then a lot of fire, non-impact, that kind of forms that tail, the far left side, the majority of safety occurrences there. I do note that I've got another system component failure power plant. That's my count F. Count F has failed me with that M dash and that hyphen. So I do apologize for that, but it doesn't change the overall effect there. So quite interesting in terms of that distribution. In terms of the lower category, so if we dig deeper into those non-power plant equipment problems, those system component failures, what do we get? The largest single one there is fuel. So a lot of the time it's the fuel system, and that's not a surprise with the Artemis scrubs that we've just had with leaks with the fuel system. It's obviously the best thing for them to do is to scrub those launches because of issues with the fuel system. Very wise, very important thing to do to maintain safety. And when there have been issues, fuel system issues is a big thing there. Other things that are listed there are the automatic flight control. So a few things have veered off because of gyros and things like that. Environmental control systems, sadly, there's been a few people killed because of problems with oxygen-rich environments and things like that. Miscellaneous systems like hydraulics and stuff, electrical systems, the actual structure itself. And again, the Colonel talked about the aluminium structure underneath. And sometimes, unfortunately, like one of the other shuttle disasters, if you get into that structural failure, there's a problem. And then flight controls actively veering things off course. Digging into that next layer of the power plants themselves, it's usually just a case rupture, and it's very difficult to code these things for rocket-based propulsion because the ADRIP taxonomy does not account for a rocket-powered aircraft. None of these subcategories also are really great for rocket-powered aircraft, and especially when you come to solid fuel rockets where the fuel storage tank, for lack of a better word, for the solid propellant is also the combustion chamber. It's very grey as to how you would code some of these things, but those engine cases exploding, so basically the rocket exploding because of a case rupture, is the overwhelmingly the most common thing there. In terms of human factors or technology, it's one of the questions that I wanted to set out to ask, and it's actually a lot less skewed than it is for hypersonics and for even for remotely piloted aircraft. It's slightly ahead, the equipment problems, but human factors is actually quite large, much higher than I would have thought. But if you think about the VSS Enterprise, the Virgin Galactic issue that happened, that wasn't an equipment problem in terms of the feathering failure for their re-entry. It was actually human factors. The pilot pulled the feathering system early, and that caused that accident. So it wasn't an equipment problem; it's human factors. So there's definitely some issues there that need to be looked at. It's not as skewed to technology, so we can't just engineer out those problems. So it's a bit of an odd choice for case study, again, after the plenary this morning, but it's the same, just refreshing. So I guess one of the things you want to do with a case study in a situation like this, if you do a post-accident analysis, is you want to find what's called the average type of case, and obviously that's average in a nominal sense rather than in a interval or a ratio sense. So we're looking for the most common thing. So the example of the Columbia accident here is it's a fatal accident in the USA. It's a system component failure, non-power plant. It wasn't the rocket that was responsible for it, and it was an equipment problem. So it's ticking the, was it 1, 2, 3, 4, 5, 6 boxes for being average, and then the only things it doesn't do is it actually sadly involved the fatalities of the crew rather than people on the ground, and it wasn't a fuel-based problem. It was actually the thermal protection system, the structural-based problem on this one. So if we could find something that involved a problem with a fuel system on the ground, that might be a bit more average, but it is a good case study concept of that foam coming off at launch, cracking into that carbon leading edge on the wing, causing the failure on re-entry. So what do we need to do? So again, ADRIP doesn't have rockets at all as a propulsion type. So electric things have been in there for a while. So piston, gas turbines, all in there. We definitely need to make sure for future purposes that we have much more information about rockets and subcategories for those. Again, rockets have specific system component failure power plant subtypes that they need, and what things that we've identified. So ignition systems, so specifically what part or what type of ignition system. So there are different types of rocket engines and different types of ignitions that are used in them. So it's very important to identify those so people can effectively compare apples with apples if they want to actually have a look at the impact of these systems. I can't remember what my EXP is. I feel like a fool at the moment. But again, it's very important for us to have that granularity in those subcategories. Sources of explosions and other structural issues. So again, a lot of these things are just explosions, and not enough information is given as to where the explosion may have come from. So it'd be good to, in the coding structure, have the ability to identify more information about where an explosion happened. And that's mostly because an explosion in aviation is just an explosive decompression. So also the thermal protection system is an important thing that needs to be included, because most re-entry vehicles are going to have a TPS. It's very important, especially when people are involved. So it's important to kind of differentiate between the thermal protection system failure and a thermal problem, which is where there's an overheat where the thermal protection system isn't, where the TPS fault would be something where there's a failure of the TPS. And staging should also be identified. So in these situations, I've presented anything here, but it's important to talk about whether it was the first stage, second stage, or third stage, depending on how many stages it is into orbit for your specific vehicle. All right, thank you very much for that. And I don't know how best to look at everything at the same time. What I'll do is I'll stop sharing, and that way I can have a look at stuff.
Thank you, Dr. Wild. We currently do not have anybody typing in
right.
questions. We will give until maybe 7 at 40. Then we will continue to Sanjuti Malik, and we will bring it over to her. Thank you for sharing everything.
Thank you very much. Thank you, everybody, for listening.
All right. Okay, I guess. Next we will have Sanjuti Malik. Sanjuti is a senior associate in compliance and strategic partnerships at CommScope, Commercial Space Operations Center, a small business that develops solutions to address current and emerging challenges in the space operational environment. arising from intentional threats as well as hazards such as space debris. Sanjuti has an LLM, Masters of Laws from the Fletcher School of Law and Diplomacy at Tufts University and has been interested in different aspects of space law, in particular space debris, mitigation, and removal, and the law of the commons. Welcome, Sanjuti. You may go ahead.
Thanks a lot. At the offset, I really want to thank you all to put together this event, and I'm really glad to be here. And Graham, what for you? I thought that was like a fantastic presentation that you had. Have a couple of questions, but I'll keep that for later. So yeah, with that, I'm going to begin sharing my screen. I hope this is all visible to everyone.
Yes, we can see this.
Okay.
Thank you.
Great. So before we begin, I want to show a short video. I'm just going to let it play for a couple of seconds. So essentially, this is a simulation that my organization put together. It depicts the 15th of November, 2021 Russian anti-satellite test that occurred. It shows the representative engagement and fragmentation field that could have been generated by this event. The simulation predicted that the generation of almost about 15,000 debris pieces, with about only 3,000 of them being actually trackable. So the debris from the Russian demonstration started creating surges of close approaches that we termed as conjunction squalls. And in some cases, tens and thousands of them were occurring with even active satellites in lower Earth orbit per week. In August 2022, just a couple of months after November 2021, we found that there were more than 6,000 conjunction squalls or close approaches involving around 841 Starlink satellites that comprise 30% of the constellation, which is an alarming number. Although we do not have the right cadence, whether or how many, if any, of these satellites that had to be maneuvered around, we can certainly state that this was a very concerning event that was taking place. So as you can see in this graph, from 2017 till about today, there has been roughly a fourfold increase in the number of times objects in the lower Earth orbit came within 1 kilometer of other objects. In other words, what I mean is very close to causing some kind of serious damage in outer space. The point here is that there is a rapid increase in everything that is out there in space, and more importantly, that these could cause significant harm in the space operational environment. Hi everyone, I'm Sanjuti Malik and I work with ComSpark Corporation. I've already been introduced, but we are basically leaders in enabling a secure, safe, and sustainable space operational environment. And our solutions are high accuracy, low latency, and high capacity for space situational awareness, space domain awareness capabilities. I will be talking about the rapidly growing population of satellites that are increasing the risk of congestion, collision, and debris generation in outer space, which in turn has heightened the need of the hour to facilitate the formation and implementation of necessary space traffic management standards, guidelines, and best practices for free and open access to space. I'm not a tech expert. My background is in law, unlike Graham, which was fantastic, but I do work with all the tech people, and therefore my discussion today is going to be centered more around the policies and laws that are surrounding this. Moving forward, so I mentioned about free and open access to space. Basically, this concept is envisioned in the Outer Space Treaty from 1967, which is a cornerstone of space law. It emphasizes and mandates that the exploration of outer space for the benefit of everyone, and stipulates that it has to be the province of all mankind. And we hope, reasonably so, that for all of this to be happening at a very sustainable rate. True to this, a quick glance through some of the major new articles regarding outer space in the very recent past has included things like mega constellations, on-orbit servicing, refueling, space tourism, increased maneuvering, anti-satellite tests, amongst many other things. Some of them were even covered by Graham in his previous presentation, where he was talking about everything that's going on with space commercialization, from mining to tourism to point-to-point travel. While this progresses and advancement in space is absolutely commendable, sustainable growth is not only welcome, but absolutely needed. However, hostile capabilities and increased congested environment in space has threatened this free and open access to space. No doubt that the global space activity is on the rise. Object population in outer space is more than 4,800 active satellites currently, which represent around 40 nations, and nearly 25,000 satellites are projected to join by 2030. Some of the other figures that are in place that NASA has counted, we have like active satellites, which are about 4,500, debris that's around 23,000, and those are like larger than softballs, so softballs that you can actually count, and 500,000 that are marble sized or even less than that. The result of all of this is that it's problematic, and this busy orbital ecosystem, which complicates tracking and coordination in outer space. The rapidly growing population of satellites increases risks of collisions and debris generation in outer space. And this has led to the outer space being correctly characterized as contested, congested, and competitive domain, which makes the space traffic management environment very, very critical. So what do we understand by space traffic management? There is no set definition that has been put in place, unfortunately, but these are some of the buckets in which these are the terms and components that are involved in it. It's essentially a robust framework for on-orbit coordination of activities to enhance the safety, stability, and sustainability of operations in the space environment. Space traffic management can also be defined as the ability of international and national authorities to track spacecraft and space debris, to regulate where space operators position their spacecraft, and to oversee debris mitigation and remediation efforts. In effect, it's a risk reduction mechanism towards sustainable use of outer space that could help reduce collisions and subsequent catastrophes, which are often becoming more and more common as launch costs decrease, increasing the number of satellites, entering the Earth's orbit. These collisions disrupt all commercial, governmental, and military services, and people think that they can threaten the sustainable use of outer space in the long term. But it's already started happening. As you can see from the Russian anti-satellite test example that I quoted earlier, and the same sort of anti-satellite test had also occurred in 2007 by China, whose remnants are still lingering in terms of debris pieces all across the in the space right now. So let's take a look at some of the current status of what the space traffic management regime looks like. In the first bucket, where we have international cooperation and coordination, we have the United Nations Committee on the Peaceful Uses of Outer Space, the UN COPUS, which adopted guidelines in 2019 for long-term space sustainability, but they lacked real consequences for wrongdoing. Individual nations, including and especially the US or major world powers, can model positive behaviors and go a step further by probably shaming those who are not following these guidelines. The European Space Agency, ESA, is leading the way with active debris removal technologies and mechanisms. They continue developing deorbiting capabilities. We do not have any international agreements to deorbit old rocket launchers and defunct satellites, unfortunately, at the moment, but we can definitely help clean up existing space junk if we did start building on these. In April 2020, the United States announced a national commitment not to conduct direct ascent anti-satellite testing, referencing the Russian destructive anti-satellite test of 2021 and the Chinese test of 2007. Currently, we have about 5 nations who have signed on to this moratorium. Lastly, we're working towards implementation of open architecture data repository and also a space sustainability rating. In a way, we're trying to find ways to incentivize participation in space data sharing so that we would just have more space situational awareness and we can arrive at a better stage with space traffic management. On the second bucket, which is the public-private partnerships, we have some organizations like the Space Safety Coalition, which is an ad hoc coalition of companies, organizations, and other government and industry stakeholders that actively promote responsible space safety through the adoption of relevant international standards and the development of more effective space safety guidelines and best practices. So for instance, the Space Safety Coalition's 2019 best practices for the sustainability of space operations was endorsed by several space industry players, including companies that are leading in deorbiting space launches, etc. It also included recommendations. One of the biggest highlights was it was recommending to quote unquote strive to deorbit all spacecraft after their orbital life, something that doesn't happen currently. Secondly, the United States and several industry actors often provide comments in forums facilitated by the White House's Office of Space and Technology Policy as well, which is a forum for several commercial actors and other stakeholders to come together and recommend policies and actions as well. However, while industry actors are able and willing to fill these technological gaps, unfortunately, the current regulatory system and the vacuum remains a challenge. So what are some of the recommendations for regulating space traffic management? Definitely an international framework is ideal, and so is a national framework for space traffic management, for protecting a future of space safety and allowing for sustainable growth in the space domain. A few recommendations that I have, first from the international lens is defining terms. Through forums like the United Nations Office of Outer Space Affairs, UNOOSA, the international community should definitely reach consensus on the definitions of what space traffic management is, what space situational awareness is, space domain awareness, and other related terms, because all of these would finally be related to what space traffic management is being described as. This will also create a baseline consensus on which to base future rules for space traffic management. So this is an absolutely necessary first step here. Secondly, to start avoiding creation of new debris. Future space activities can take advantage of cutting edge technological developments for maneuverability. So we have things like protective mesh for propulsion, etc. Additionally, space operators can be encouraged to sign up to the space sustainability rating tools that allows operators to evaluate their collision avoidance process, their trackability, and their data sharing practices, among other things. These are all expected to roll out soon. All the research bit is done so far, but if you follow the news, I think by the end of this year, it should be rolled out in effect. Thirdly, improving space situational awareness. While stakeholders do understand the benefits of space, our ability is still kind of limited to detect and track things that are in space, and therefore to provide accurate and precise timely warnings to space operators. What happens is the exquisite scientific and national security sensors While they can be trained on specific space objects in a crisis situation, but their resources are still limited and may not be able to actually cover the millions of pieces of space debris that threaten operations. Therefore, the recommendation is that it's highly important to allow the commercial ecosystem to lead this effort, as opposed to all of the SSA being just with governments and military across the globe. Next, establishing space traffic coordination and management guidelines, which is we can come up with a set of simple rules of the road that operators should follow when they are at risk of collision. International tensions are likely to generate near-term diplomatic progress, so the private sector is likely to generate practical ideas and best practices that should ultimately inform international space law and policy. For active debris removal, we have like the European Space Agency and Japan that are funding active debris removal missions, with strong indications that others may also follow. While there remains both technical proof of concept for such best ways to accomplish this, we have like magnets, nets, harpoons, clamps, etc. We have a few important legal policy challenges to overcome, such as who can move our captured debris, or what authority can have authority over such things. So we must take steps to address these, and not only to suggest them, but also put them in an implementation format. It's also important to assign liability. So to manage and protect national space assets, accountability must be assigned for both man-made and naturally occurring space debris. Just because we are able to, or some stakeholders are able to dispose defunct satellites to graveyard orbits, which are orbits distant from commonly used ones, must not be considered of lesser importance. That too is required to be cleaned up as well as reprimanded, and those stakeholders must also be held responsible for such activities. As a next point, establishing minimum standards of conduct. The Outer Space Treaty lacks proper consideration of traffic management and collision avoidance. This regulatory gap provides the opportunity for space entities to write the rules of the launch and maneuver of satellites right now. So prior to launching, for instance, national and international governing bodies might consider confining satellites that lack maneuvering capabilities to specific altitudes. It's easier said than done, but adding exceptions can be a way forward to capture all sorts of scenarios as well. Moreover, when operating above a specific altitude, spacecrafts should be required to meet more stringent safety requirements as well. The last one on this is coordinating an authority to lead on space traffic management. So to establish a coordinating authority, discussions should begin in existing international fora like the UN OSA. Eventually, a coordinating authority might expand or mirror existing governing bodies as well. For instance, creating an international civil aviation organization to monitor space activities would be a great step forward. Moving towards the more domestic and US-centric views on some of the recommendations that could be set in place is allocating responsibilities and authorities. So in June 2018, the White House issued the SPD3, the Space Policy Directive 3, which is a national space traffic management policy, which called for a new approach to space traffic management and charged the Department of Commerce with the responsibility of data sharing and collision avoidance support services. In fact, this month, August 2022, the Department of Commerce and the Department of Defense in the United States signed a memorandum of agreement to support the Department of Commerce's leadership on a civil structure of space situational awareness, which is a fantastic step a step closer to having more set guidelines for space traffic management eventually as well. Industry representation is an absolutely important feature to be out here, where industry leaders can or must be represented on different forums, incentivizing adoption of best practices. So we have the Federal Aviation Agency space launch licensing requirements that can be updated to include requirements to report planned maneuvers as well. And operators should be further incentivized to demonstrate deorbiting and debris mitigation capabilities. Both these measures can help mitigate the risk of collisions. Having said this, it would also be best to have like prioritization over incentivization. So the US and several other countries should definitely rally the international space community to determine a common set of rules surrounding the disposal of defunct satellites. The burden should be placed on satellite operators to provide solutions on space debris removal as well, and not just incentivizing them for going and doing the removal. We must also prioritize the sustainability of outer space by making sure that every technology advancement that we make, they're also fit to make sure that the solutions of active debris removals are also fit within their capabilities as well. And lastly, lastly is to lead by example. Well, the United States could definitely lead by example in outer space by sheer virtue of being one of the major spacefaring nations. The US departments and agencies can encourage international cooperation by incentivizing positive behavior or discourage malign actions by leveraging sanctions. So in the end, whether we will actually ever be able to assure zero collision risks in space is a moot point. For this zero collision state to occur, there are possibly only two solutions that can eliminate our risk. Either we conduct zero activity in space, or we limit new activities in space to such an extent that we have highly restrictive and controlled space traffic management frameworks. In my opinion, neither option is practical, nor would they be acceptable. In today's world, we are majorly dependent on space-based services like weather forecasting, Earth monitoring, GPS, telecommunications services, etc. I mean, can we imagine a day without having, say, internet, TV connectivity, or not knowing the timing of aircrafts, ships, etc.? The answer is a plain simple no. So our national security, economic growth also depends on the free and open access to outer space. If best practice standards, rules, and policies do not advance at the same and as quickly as technology, then we will jeopardize our own access to space and all the benefits that we derive from it. So I do not want to end on like a grim note at all. We are making good progress. So these are some of the steps where world is moving towards having some sort of guidelines set in place for space traffic management. We have more and more countries, we only have 5, but more and more countries are coming together to declare a moratorium on anti-satellite missile tests. We also have industry leaders coming together to form like that, to opine on and write satellite orbital safety best practices. We saw that the DOC and the DoD in the United States have finally put it down on paper on a memorandum of understanding on how space situational awareness can be. And they're also moving towards putting it on the commercial as opposed to only keeping it with the government, which is a great step forward. We also see that the United States is formally adopting tenets of responsible behavior in space. We have the National Orbital Debris Implementation Plan that's also getting, that was just released and getting implemented soon. NASA is funding projects to study orbital debris. And then we also had the newest bill that was introduced called the Orbits Act for making sure that we do not endanger the future of space exploration. All in all, to suggest that we are moving and tending towards the right path. While we have several things in place, I think it's also extremely important for us to start implementing. We're never going to reach a place where we have all the policies set and then all we have to do is implement. Both of these will have to go on a simultaneous footing and move parallelly. Now, there can be a top-down approach or a bottom-up approach. Top-down would be that the United Nations and international organizations frame policies and rules, and then they trickle down to countries and to the stakeholders below them. The bottom-up approach is that if the private industry is taking the lead and doing so many activities in outer space, they can be recommending frameworks as well. So neither of these two exclusively is going to work. So in my opinion, where we can see a meeting point is if both the top-down and the bottom-up approaches come together somewhere midway. Therefore, on a last ending note, what we should aim towards is the implementation, because right now we've talked so much about policies and so are governments and the international organizations. We all recognize what is happening and that there is a dire need for bringing them into place. So let's start acting. And with that, I would like to thank you all for your time and happy to take any questions that might be there.
And Judy, we do have a question from Tim. Thank you very much for the presentation. What do you believe stands in the way of widespread adoption of codified STM principles among the international community, and how can those obstacles be overcome?
I'm sorry, your voice is a little bit choppy. Do you think? Let me take a look at this.
Okay.
No, it's okay. 1 second, maybe I'll just take a look at the chat. Oh, it's not in the chat. I'm sorry, could you?
No worries. Let me repeat this one more time. What do you believe stands in the way of widespread adoption of codified STM principles among the international community, and how can those obstacles be overcome?
Right. Thanks a lot for this question. So I believe that one of the biggest challenges is that most countries have not signed on to it, right? That's with every international treaty or guideline that gets set in place. So you have to be signatories first, and then you have to also ratify them. So first, when you sign on to it, then each country is saying that, yes, we agree to the terms. But when you ratify is when you're actually implementing them in your national legislations. So without these two steps actually happening, we are unable to see its effect taking place as much. So according to me, that's like the biggest challenge that is in place with the guidelines. And second, also on a practical scale, is economics and the finances that would be required to really make sure that STM also happens. So while we can, in the first step, make sure that we do not generate more debris, then there's also a second step to make sure that you're accountable for everything that is already there in outer space, and you should be able to withdraw it. So that costs a lot of money, like finances, which companies or countries are not willing to spend towards at the moment. And thirdly, space traffic management would also mean that you're clearing out things that are existing in space, which are just debris. There is a national security angle to it, which is that if X country has its objects, can a Y country's technological capabilities go out there and bring it back? It's not acceptable currently, unfortunately. So because it can have potential important data from another country. So if it gets into the adversary's hands, then you're always wary of what sort of consequences the national security realm can have. I hope that was answering some of your question. If I missed something, please just feel free to probe me more on it.
Do you mind if I ask a question?
Go ahead, Graham.
So what is your thoughts on how to deal with companies that are effectively refuse to pick up the phone in a close encounter situation and don't want to move their satellites, and then make the more responsible person take corrective actions? Because that seems like a very unsustainable way for business practices to continue in the future.
Yeah, that's a fantastic question. Thank you for that. So the space traffic management guidelines are also talking about assigning liabilities, right? So if you're not picking up the phone, then you're also liable for it. We have the space sustainability rating that's coming into place. And one of the criteria is how you're getting scored or marked is that you would be responsible for doing such acts and being responsible. You pick up the phone, you maneuver in time, you do such things. But again, I think the biggest problem is not being able to implement it yet. Personally, I do think that we have enough policies. We have enough guidelines. We're talking a lot about it, but where we're failing in the implementation, or maybe we're just not fast enough because the technology is just like rapidly moving so fast that we're not like catching up to it yet. And I don't know whether we're just waiting for something really bad to happen for us to like take that step. So that's like a catch-22 we're in, but we must definitely do it. And one way, and I think that's like an easy way, according to me. Well, international leaders may not think that, but if something like this happens and you don't pick up the call, or you don't act that is a best practice in a best practice mechanism, then what other countries should do is reprimand them, put sanctions. Okay, you may not like go towards economic sanctions, but you can always reprimand. You can always state it internationally. I hope that was somewhere close to what you...
That's great. So I like to think about the analogy always back to aviation, and at the beginning of the industry, like the 1918, I think was the first airline. They really did have free reign to do whatever they wanted. And I'm sure some companies are going to complain soon as more regulations come into play to say, why can't we just do business as usual? And the whole point is business as usual is unsustainable. And not picking up the phone deliberately is a critical safety issue, and you're going to cause an accident at serious cost to so many different people. So just quickly, I've got a question in the chat for me. That is, as an air traffic controller, we use NASA reporting site to report safety issues. Has NASA set up the process for space traffic as well? I do have some students, some third-year project students at the moment, who are looking at the NASA ACARS website. I think it's called ACARS is the name of it. I think, or maybe I'm getting confused with another acronym. But they're going in there and actually getting one of my students is looking at axioms for air traffic controllers, because that's what she's going to do for the Air Force. And I don't think in there are options for you to pick space-based things. So it's a voluntary reporting system, so you can go into it, but I don't think there is anything in there to specify a space-based operation as of yet. So yeah, that's kind of exactly along the lines, Tony, of what needs to happen. Obviously, I'm not saying it needs to happen in the next few months or anything like that, but it needs to be there so we can collect as much information as possible. And to be honest with you, the sooner we do it, the better it is, because if, like I said, if we can learn from those little incidences and there's the ability for people to report anonymously, it's a great system to be able to get that information sooner rather than later. You've got another question from Jason, by the way, which is regarding active debris removal. Do you think organizations like NASA will take the lead, or will it fall to private companies to take the reins?
Do I think whether NASA will take the lead? I don't know. Whether I think NASA should, definitely yes. NASA and the United States and every major space-faring nation, but more importantly, the United States, because we have, well, the United States has the maximum number of satellites in space. So if there's anyone who can start taking actions, it's the United States. They also have the maximum number of private companies that are in space. and are planning to also be there in space. So in my opinion, the best amalgamation that would work, and the United States does that too, is that you take inputs from the private industry and then implement it as policies, guidelines, regulations, and then like scale it up for the international community to consider. One small example that they have been leading with is also the moratorium for anti-satellite tests, to make sure that, you know, they're inviting other countries to also sign on to it and eradicate it, or at least like just put a stop to it. They started themselves, and now in the past 1 year, I think it's been like 5 countries. You can't have like the adversary nations to, like, you know, China and Russia to easily just come up and say like, yes, we'll sign on to something that the United States just put forth. But that's a positive step forward.
Yeah, again, it comes back to not specifically a NASA, but an international version of NASA. So like ICAO, the International Civil Aviation Organization, you need an international civil space organization that's doing that rather than coming along with it. One of the other things I'd like to talk about as a physicist who loves nuclear power is the issue with nuclear power is actually decommissioning. And sadly, decommissioning of a nuclear power plant happens after the energy company's made all of its money. The same thing's true of space operations. When your satellite's now worthless in space because it's not doing what it's supposed to do, it's no longer worth money. So that cost to deorbit at the end of its life is a very big detractor. And I think there probably needs to be some upfront costs of putting things in space. How would you feel about that?
So the cost is something that we just are unable to like go past, right? Like we can put the policies, guidelines in place, but who is going to fund it? Well, private companies have started, like you have so many private companies that are doing, that have the technology for active debris removal, but are they like actually going out there and doing it? Twofold, the cost, who's going to fund them? They do want nations to fund them. They don't just want random people to fund it, and nations are not there yet to fund such expensive missions. And secondly, again, I think it's challenging each time that we talk about national security, because it's like really sensitive waters to be treading on. Like if you perhaps take one material that what would you call as national security? Then you start defining them. Can this material be considered, or can this material not? Like the United States also has policies in place that if like a debris piece falls on your land, you can't just keep it.
Yeah.
You'll be imprisoned or you'll be fined for it. So the cost benefit analysis, I think, far supersedes the damages that can occur with a satellite not being there or getting damaged, as opposed to the cost that will be spent in sending them. And we just need to be willing to take that step. And maybe there needs to be like some external push that comes faster.
Yeah, definitely. So I can see it in the long term, in the future. I could see it as a solution in place, but it'll be interesting to see it get turned on and how much people complain about it when it happens in terms of that forward planning for decommissioning of satellites. Thank you, Tony, for answering the question about what the acronym for the database is. Are there any other questions people have? Interesting. The number of people in the audience has grown during question time. So.
Oh, interesting.
All right, we probably have one more question. We have one in the app right now. It says, give me one moment. Has NASA set up this process for space traffic as well, or is it primarily for air traffic? Also, with the Department of Commerce taking over space traffic control in the US, how do you see the future of space traffic control globally?
I think that's for you, sorry.
Oh, okay. Can I just note down, because there were like a couple of things there, because I don't think so. What I understood, whether NASA has taken over space traffic management, is that?
Yes. So has NASA set up this process for space traffic as well, or is it primarily for air traffic? And with the Department of Commerce taking over space traffic control in the US, how do you see the future of space traffic control globally?
Right. Thanks for this question. So NASA has not taken over space traffic management. I wouldn't be able to really talk about air traffic, and I think I will just like leave it to Graham for that. I'll defer to him for that. But space traffic management, space situational awareness, it's all been in this realm where it's sometimes Department of Defense, sometimes it's Department of Commerce. But since the beginning of this year, it has we have seen, and this month we also saw that the memorandum of understanding that's being signed between the DoD and DOC, that all of the commercial aspects of space traffic management, space situational awareness, and the reason why I'm using both these terms is that because we haven't like specifically defined them and they would all be related. So STM, SSA on the commercial side is going to be all DOC, just to make sure that DoD is not getting overwhelmed with all the other things that they have to do for national security. So everything that's going to be national security sort of oriented, that's going to remain with DoD. And what I mean by that is there is the term called space domain awareness, and that's the distinction that's made. So between just space situational awareness and space domain awareness. So everything that's SDA falls within DoD, and everything that becomes SSA and like commercial is within the DOC. I hope that like helps you get a better understanding of where we stand with that. So like none of these entities are singularly just taking away each other's contribution towards it. It's still going to be there. It's just going to get divided in terms of intent and the objective that's being achieved, whether it's commercial or defense and national security. And the primary question on whether NASA has taken it over, no, NASA hasn't really taken over on that. Yeah, they do a lot of research, and they've also started funding, they're putting in more funds towards like orbital debris mitigation, research work across universities, companies, etc. But it's not getting siloed within their organization.
Thank
If I
you
missed
so much,
something,
Jyoti.
please just let me know. Or yeah, I think we're also about over time, and I think Graham would also agree with me. You guys are free to reach out to us with more questions. Happy
Yeah,
to
definitely.
answer
Thanks for
them.
coming, Jyoti.
Yes, thank you,
Yeah.
Thank you, Dr. Wild and Sanjuti. And we will end the call now. And we would like to invite you to the next session, which is in about 10 minutes.
Okay. Thanks a
Thank
lot
you
for
all for
organizing this and everyone's time. Really appreciate it. Have a good day.
Thank you.
Thank you. Bye-bye.
Bye,
Bye-bye.
Graham. Very nice to meet you.